Good morning and welcome to the third of 3 videos on chapter 2 in your textbook. Today, in this video, we're going to look at the differences between what we call a correlational study and an experiment. Now, we'll talk about the actual definitions in a few moments, but generally speaking, a correlational study just looks at two variables and tries to determine whether there's a relationship between those two uh, uh, variables. In an experiment, one of the variables is manipulated by the researcher to determine what the effect on the other variable is going to be. Generally speaking, in a science course or in a scientific study, we use experiments because we're looking for the cause. All right, we're trying to demonstrate that the effect of one or the action of one has an effect on the other. Now, the way that we talk about this is in terms of what we call a research design. And any study, any research that's being done by a social scientist or a psychologist or anyone else is simply the way that the study is laid out. Right? How do we design this study? How do we put it together? Okay. And as I said earlier, there are two major types. All right. Correlational studies, generally speaking, are just looking at variables without manipulating. The observer, the researcher, is kind of hands off. They're not doing any manipulation of the data. They're simply collecting the data to determine whether there's a relationship between one and the other. One variable and the other. In an experiment, a researcher more specifically has a certain hypothesis. They believe that X causes a change in X causes a change in Y. They're looking for that cause and effect relationship here. So, for example, a correlational study might look at the relationship between the height and weight of people. All right. You would expect that taller people, because they have more body length, would also have more weight. And so, you gather 100 people and you measure the height and weight of every single person, and you draw a graph and determine whether there's a relationship between height and weight. You would expect that you'd probably find a relationship. A relationship that looked something like this. And now it might have a lower slope, it might have a higher slope, who knows? In an experiment, you're trying to determine the differences between two groups of people or animals or whatever, and trying to determine if you manipulate a certain variable, does it have an effect on the measurement of the other variable? All right. In an experiment, you might try to determine weight loss versus certain diets. All right. No diet, and there's this much weight loss. The keto diet or the paleo diet or whatever it is, you might get that much weight loss, and you compare the difference between the two. All right. So those are the two major types of designs. All right. So in an experiment, the researcher actively changes or manipulates one variable and then measures the participants' scores on another variable to see if there's a relationship produced. All right. As I said, you may graph this and have certain kinds of diets over here. And we've got diet A, we've got diet B, and maybe diet C is the control. All right. No diet at all. Okay. And so over here, you might graph weight loss. All right. And you may find that with diet A, you lost 10 pounds. With diet B, the average participant lost 20 pounds. And with diet C, the control, people lost 6 pounds. Okay. And so the researcher in this case has actively changed or manipulated one variable. That variable would be the diet, all right? Maybe everybody in group A only ate lettuce leaves, all right, for a month, all right? And everybody in diet B only ate peanuts for, the entire month. And in the control group, the folks ate anything they wanted to, all right? And so that's an experiment, because the researcher is changing the variables, the diet in this case, in order to determine whether there's an effect on weight loss, right? And so what they're really doing is trying to determine whether a relationship is produced, right? Do we see, a cause and effect relationship here? Now, in terms of an experiment, there's always two variables, all right? The independent variable refers to the variable that is changed or manipulated by the experimenter. So in the example in the previous slide, the independent variable there would be the diet, okay? And so you are specifically manipulating that. You're giving group A one diet and group B another diet, and possibly group C a third diet. Okay, those are the variables that the researcher is actually changing, manipulating. All right, varying. Now, each of the possibilities is what we call a condition. Okay, so a condition is a specific amount or category of the independent variable that creates the specific situation under which participants are examined. All right, now the conditions in the previous experiment were diet A, which was all, what did I say, lettuce leaves. Diet B was the diet where everybody ate peanuts, and diet C was the control, where there was no change in the diets at all. So those are the three conditions that exist in that imaginary experiment that I described in the previous slide. A condition can also be called a level or a treatment. Right? So treatment A is the lettuce leaves, treatment B is the peanuts, and treatment C is the control in that example. So the independent variable can have multiple conditions. It doesn't have to just have two. Although, quite frankly, the simpler an experiment is, the more powerful the results tend to be. So you compare a diet versus a control, rather than comparing multiple diets. Now, on the other hand, the dependent variable measures the participant's behavior under each condition of the independent variable. All right. In our example, we talked about how much weight each person would lose given that diet. And of course, you don't just have 3 people, you have, 10 people in each group. So maybe 30 people participate in this experiment. And so when you do that, you have to take an average. But the measurement, what you're measuring at the end of the experiment, or maybe all the way through the experiment, is the dependent variable. In this case, it would be the weight loss that the group experienced as a whole. All right. So the dependent variable measures a participant's behavior under each condition. All right. Condition A, condition B, condition C of the independent variable. All right. So again, it's what you are measuring there. And all experiments need to have at least 2 different independent variables, all right, or conditions, treatments, and one dependent variable, the outcome, the measurement that you're making in order to quote unquote prove your point, if you will. All right. So independent variables and dependent variables, very important to consider when you're designing an experiment. Okay. Now, a correlational study is simply measuring participants' scores on 2 different variables and then determining whether a relationship is present. So in this case, all right, we talked about the height and weight aspect. All right, we put height here because height is generally genetically controlled. All right, how tall you are is based on what's called the mid-parent height. So you take your dad's height and your mom's height at adulthood, take the average of them, and then you add 2 inch. I think it's 2 inches for males to that average, and subtract 2 inches for females. I believe that's the generally accepted formula nowadays. But your weight is dependent upon how much you eat, right? Um, calories in, calories out, that sort of thing. And so, you might find a data point here and here and here and here and here, and here. All right. And something like that. And so in this case, all right, there's probably a weak relationship here. As height increases, weight increases as well. Now, are there some very skinny tall people? Yes. Are there some very heavy short people? Yes. Are there some very skinny short people? Yes. Are there some very heavy tall people? Yes. All right. But on average, in a correlational study, we're looking for that relationship. Is there a trend? As X increases, does Y increase, decrease, or remain the same? Okay. Generally, in a height-weight comparison, we would expect that as height increased, weight would increase as well. Now, the real key to an experimental design is to try to determine causality. In an experiment, we in either one of these things, we don't try to prove that the independent variable causes a change in the dependent variable. All right, and what we do try to do is try to show that there's a relationship between those two. All right. So in an experiment, we cannot definitely prove the independent variable causes the scores on the dependent variable to change. It's always possible that some other hidden variable is actually the cause. All right. There's a great example of this in your psychology textbooks for science. Right. There's a hidden variable deal. A study, I think it was in Japan, showed that people with college educations made or had more money and or had showed more or they had more appliances in their house, more stereos, refrigerators, and that sort of thing than people without a college education. Well, it turns out that the difference in reality is the number of children, the later they got married, and that sort of thing. So there are other things that were affecting it. It wasn't just the fact that college educated people had more stuff. It was that that they had waited longer in life to have children, get married, and that sort of thing, and therefore they were able to afford more of that stuff. They had saved for longer. Now, a correlational study doesn't even try to identify the cause. It just describes the relationship. And so if you think about these two, experiments versus correlations, an experiment is certainly a much more powerful method of trying to glean a cause and effect relationship. Okay. So for the next thing that we want to talk about here, we're going to talk about characteristics of scores. All right. And when we do this, I want you to be aware that there are different ways of looking at numbers. All right. Most of us just think, oh, numbers are numbers, and there it is. But that's not really the case. Sometimes scores are simply names and labels, and at other points they're actually measurements of specific data points. And so you have to be very careful that you know what the characteristics of scores are when you're looking at a data set, especially one that's being presented by somebody else. Okay, so the two most important characteristics of variables are first, what type of measurement scale is involved? What are we using here in order to uh, base our conclusions on? And finally, whether the scale is continuous or discrete. Now, in terms of the types of measurement scales, we're going to go into detail on all of these things, by the way. But the type of measurement scale, there's 4 different kinds of scales. All right, there's ones where the numbers associated with a score are simply names. Okay, and that's the weakest of them. And then finally, you make your way all the way up to the point where the scale itself is a number that specifically represents a very specific data point. All right, and we'll get to all of those in a moment. The other thing here is whether the scale is continuous or discrete. Okay, and what this means is if a scale is continuous, that means that every possible measurement is in there. Every decimal, every possibility. If you're measuring, for example, the height of your population, then you can have somebody who's 6'2.25", 6'2.5", 6'2 and 3/8", and whatever. And you can get right down to the hundredths or thousandths place in your measurements. Discrete measurements tend to be things that are either or. All right, you are either male or you are female. All right, there is no in between, and so that would be a discrete scale. And so, if you're doing an experiment that involves measurements, those measurements you have to determine whether the measurements are on a continuous scale or on a discrete scale. Now, there are 4 kinds of measurement scales. All right, and their names are listed here. Nominal simply means names, okay? And that's what this is. So the numbers associated with this measurement scale is simply a name, okay? For example, if you were to assign the number 1 to anybody who is a Democrat, and the number 2 to anybody who's a Republican, and number 3 to anybody who's a liberal, and number 4 to anybody who's a conservative, and number 5 to somebody who's independent. All right, those numbers have nothing to do with good, bad, or indifferent. It's not anything but a name. In an ordinal scale, it's simply ordered. All right, and so you put the tallest people on one side and the shortest people on the other. Interval scales are meaning that one number is different than the other by the same amount. So 1, 2, 3, 4. 3 is 3 times bigger than 1, or at least 3 intervals, all right, bigger than 1 interval. A ratio scale is when you actually have a 0 point, all right, where you start rather your scale at 0. Okay, so let's move on and talk about each of these a little bit further. A nominal scale does not indicate an amount. Rather, it is simply used for identification or as a name. All right. Examples here: hair color. All right. We'll make blondes 1, brunettes 2, redheads 3, and so on. Okay. So the number is just a name. It represents that particular scale. So if you are blonde, you'd be assigned the number 1. If you are a redhead, you'd be assigned the number 2. If you are a brunette, you'd be assigned the number 3, and so on. It's just a name. All right. And the political party example I gave you a little while ago. All right. If you're a Republican, you're number 1. If you're a Democrat, you're number 2. If you're a conservative, you're number 3, and so on and so on and so on. So the numbers that are associated with these measurements don't indicate really an amount. Okay. They're just names. And that's where the word nominal actually comes from. Now, an ordinal scale indicates rank order. Okay, there is not an equal amount separating every pair of adjacent scores. So your class rank, all right, if you graduated with 100 people and you're number 91, that your overall high school average may be an 82 average, and the person who ranked 92 in your class of 100 people might have an 86 average, and the person who ranked 93 might have a 91 average. There's not the same amount of uh, grade point average between each rank there. And so you're simply putting people in order based on their scale. Election results: who came in first, who came in second, who came in third. For example, in a primary election, well, the first person might have gotten 50% of the vote, and the second person might have gotten 40% of the vote, and the third person might have gotten 10% of the vote. Okay, there's a big difference between number one and number two and number three. All right, but they're ranked 1, 2, and 3 on an ordinal scale. Okay, so we just put the numbers in order. Now, an interval scale indicates an actual quantity, all right, and an equal amount separates adjacent scores, all right, but they do not have a true zero, okay? So, for example, the temperature scale, the Fahrenheit temperature scale, there's the same difference between 51 and 52 degrees as there is between 81 and 82 degrees, right? 1 degree is the same change in temperature. However, you'll notice that the Fahrenheit scale goes to 0 and below. You can have negative temperatures, all right? And so there's not a true 0 there, unless maybe you remember from your chemistry course, the Kelvin scale. If you took chemistry in high school, the Kelvin scale actually goes, or starts rather, at absolute 0. Okay, and so that one is a ratio scale. Celsius and Fahrenheit are actually interval scales. Okay, the IQ score, your intelligence quotient, is an interval scale as well. There's no true 0. Nobody's got an IQ less than a certain amount. I don't know what that. Honestly, IQ tests are probably meaningless, to be honest. But they don't start at 0, and so an interval scale doesn't have a true 0. Now, the most useful of the 4 scales is the ratio scale, and this reflects the true amount of the variable that is present, because the scores measure an actual amount. All right, there's an equal unit of measurement, and 0 truly means that none of the variable is present. All right, income is a good example of this. All right, if your income is 0, that means you're not bringing in any money at all. If you're bringing in $10 a week, that's your income. But if you're bringing in $20 a week, that means you're making twice as much as the person who's bringing in $10 a week. And so you can compare, using a ratio, the income of each of these people. The same thing is true with height. A measurement of length or height starts at 0, right? Although there's no people who are 0 inches tall, but height does start at 0, right? You can have a length of 0. And then 1 and 2 and 3 and so on. So it's a ratio scale. All right. So nominal, ordinal, interval, and ratio. Those are the 4 different scales that you can use in measuring. All right. So it's important that you know what kind of scale you're actually working with when you make measurements, or when you read a scientific study that is reporting measurements. Okay. Now, another thing that you need to keep in mind is whether the measurements that you're making are discrete or continuous. All right, so there's 2 different ways that you can look at this. All right, a continuous scale allows for fractional amounts, and so decimals make sense. Okay, and so, for example, if you're measuring height, okay, not everybody who is 6 feet 2 inches tall is really 6 feet 2 inches tall. Okay. In reality, there are some people who are 6'1.5", 6'1 3/4", 6'2", 6'2 1/4". All right. All of those people are lumped into the a 6'2" measurement, but it's really a continuous scale. And if you put two people, one of whom is 6'1.5" and one of whom is 6'2 3/4", if you put them back to back, you'll see the difference there. So there's a continuous scale in height. Okay, so you've got short people and slightly taller people and slightly taller people and slightly taller people. All right, and so on. And so you can see there's an increase in height, and it's a continuous scale. On the other hand, in a discrete scale, only whole number amounts can be measured. All right, and so male or female. All right, I know that's a sexist drawing, but you get the idea. All right, it's males are 1, females are 2, or not to be sexist, females are 1 and males are 2. Okay. Now, that leads us to a discussion of what we call a dichotomous variable. Now, dichotomous is a big Greek word that simply means 2. Okay. A dichotomous variable has only 2 possible categories or scores. All right, and examples of this are male or female. All right, there is no in between. You are either genetically a male or genetically a female. All right, and I don't want to get into the social implications of surgeries and that sort of thing. All right, you're male or you're female, at least in terms of for the purposes of this argument. Yes or no answers. All right, my son Stephen is infamous for. I'll ask him, did you finish your homework? All right. And he'll say, well, I did. No, this is a yes or a no question. I want to know what the answer is. It's either yes or it's no. Okay. Correct or incorrect. All right. 2 plus 2. All right. If you wrote 4, it's correct. If you wrote 6, it's incorrect. All right. And so that's the, a dichotomous variable, correct or incorrect. All right, so keep that in mind as we go through the rest of the course. Okay, now this is simply a chart of the measurement scales, nominal, ordinal, interval, and ratio, and some examples of these. Notice that they get more and more specific as you move from left to right. What does the scale indicate? From quality over to quantity. Is there an equal unit of measurement? Is there a true zero? How might the scale be used in research? And additional examples. Okay, and so on. So have a look at that chart. Now that brings us to the end of our discussion of Chapter 3. And so your homework for next class is to do the application questions at the end of Chapter 2, beginning with number 13 and running through number 25. All right. Please, again, odd numbers only, and the answers are in the back of the book. All right. Now, don't just copy the answers. I want to see your work, but you can use those answers as a guide for any questions that might confuse you. Okay. So that is the end of our discussion of Chapter 2. This is the third of 3 videos, and I hope you learned something.